Okay, on this next show, we're going to talk about our sun. And you see our sun here from the International Space Station. And we all think of our sun as a yellow star. It's even considered to be a yellow dwarf star. But from space, as the astronauts will tell you, the sun is white, visually, very white. We see it as a yellow star, mostly because of stuff in our atmosphere, pollution and haze and whatever else causes the sun to look yellow. But out in space, our sun is pretty much white. And on this next slide, here we go, is another look at the sun here. Very active place, the sun. And our sun is 93 million miles away from us. And the sun's about 864,000 miles in diameter, a little less than 1 million miles in diameter. It has no hard surface. It's basically a ball of gases and plasma. And the plasma is when the electrons have been ripped off the nucleus, and they're basically free electrons flying all around. And when you have the nucleuses and you have separated from that the electrons, together those two, it almost acts like a liquid, the plasma, as you watch it on the surface. And we got another photo here in the X-rays. Again, a very active sun surface here. We can't see this with our eyes, but in visible light, but X-rays we can see here. Just a lot going on in the surface of the sun. A lot of heat rising, causing the surface to be very turbulent. In this next slide, we have another vision of the sun. And the sun rotates at different speeds. It's quicker at the equator than it is at the poles. And so that causes a lot of really strong magnetic fields. Actually, the magnetic field is caused by a layer between the convection zone and the radiation zone that's kind of sloshing around, and that's kind of forms the magnetic field. It's a really strong magnetic field, different magnetic fields in the sun. And they cause loops and solar flares. Now here we get to the interior of the sun. And you see there's different layers. There's basically 6 distinct layers. And we have the corona, which is the outermost part of the atmosphere. Then we have the chromosome, which is a really thin atmosphere of the sun. Then we get up to the photosphere, and that's the actual surface of the sun, part that we can see. And then you get into the interior. In the yellow, we have the convection zone, and then below the yellow, in the darker orange there, we have the radiation zone, and in the blue, we have the core. And the core, again, is where the action's taken apart. Now, the core of the sun, it's about 20 to 25% of the diameter of the sun. So it's fairly large of the sun. And again, the atoms are just being crushed there, and that builds up the temperature. This core of the sun right now is about 27 million degrees. Very hot in this, and that's causing the fusion to happen very fast. Like I said, over 600 million tons every second is fusing within the sun. It's been doing that for 4.5 billion years. It's going to continue doing that for another 5 billion years. Again, just like the red dwarf stars, that's where the fusion's happening. And go to this next slide here. We'll show you the same diagram with the atoms. 2 protons. We ran through this on the first half of the show. But basically the same thing, and you end up with a helium atom at the bottom. Now, next we're going to talk about the radiation zone. And then we have the core here, and then this region over here is a radiation zone. And as the photons are formed in the core, they finally escape the core, and they want to reach the surface. They want to get out of the sun. And the first thing they got to pass through is the radiation zone. And the radiation zone is just packed with neutrons and protons and some molecules and free electrons. And what happens as the photon, the gamma ray, starts entering the radiation zone, it starts moving up, and then it runs into a proton or a neutron, and it gets redirected, or sometimes, and it basically does this loop. It's going up and down like a giant pinball machine, up and down. It gets knocked over, reflected by a proton. It gets then an electron. It basically does this thing over and over. It's going up and down, up and down, up and down. And it can take up to 170,000 years for that photon of light to finally make it out of the radiation zone. This is kind of the trip it's going to make through it. It's basically up and down, run into an electron, be pushed down. Sometimes it's pushed up, and it does this. Like I said, it takes 170,000 years to finally get out of the radiation zone. And so, like I said, after 170,000 years, these photons will finally reach the next zone of the sun to get out, and that's going to be the convection zone. And here we go. We got the radiation zone here, and now this band here, the radiation zone. And now the heat needs a new way to escape the convection zone. I don't know if I said the convection zone here, but convection zone is where this is going to go next. It needs another. The light needs another. The heat needs another way to escape, and that's going to come in convection, just like the red dwarf I showed, just almost like a boiling water. As it's going to leave the radiation zone, enter the convection zone, really hot, and it's almost like a lava lamp. It's going to make a tube of hot plasma, and it's going to rise to the surface. And that could take about another week for it to leave the bottom of the convection zone and to reach the top of the convection zone. And then once it does go through that, it'll reach the surface. And when it does reach the surface, that heat and the plasma, we'll show you on this next video. All right, in this video, we're looking at the photosphere, the surface of the sun, and you see how the convection is boiling up and causing these things. And you can notice this, like this I was talking about earlier, the center of them is kind of bright, and that's the hot area, and the edges are darker, and that's where the cooler plasma is falling back into the convection zone. It'll fall through back down the convection zone, heat up again. And so what's that look? Very active of the surface. As you see, in each one of these is about the size of the state of Texas, each one of these granulars. So a lot of movement on the sun here, and there you go with a video of that. And also on the surface, we have the sunspots. Now, the sunspots pretty much go on like a 11-year cycle. During the 11 years, they go from being really weak and not many sunspots to no sunspots, and then it'll all of a sudden be lots of sunspots, very active surface. And in this next slide, we show a close-up of the sunspots. Here we go. And this one here is about the size of the Earth, so how large these things are. And you notice the two different color differences here. The black spot is the hottest part of the sunspot, and that's called the umbra. And then you have the orange, cooler areas on the outside of the umbra, and that's the penumbra, just like the moon is called. So that's what a sunspot is. The sunspots, it's basically these tubes come up, and it basically is very low magnetic activity in here. Or actually, it's very cool, the heat. And what these sunspots do, the tubes of heat come rising up from through the convection zone. When it reaches the surface, these sunspots prevent it from coming up to this area, and that's why this area is cold. The convection's going around it, but not in this area here, so it's very cool. And there's usually there's usually two of these. They come in usually pairs. And one's will be a positive side, and another side will be like a negative side, and these makes loops. Other things to watch out for on the sun's surface, besides the sunspots, are these coronal holes. We got one up here on top, and we got one here down below in the southern hemisphere of the sun. And those dark areas, they can release huge amounts of radiation. They can have huge mass coronal ejections. What we don't want is one of these pointed at the Earth when that happens. And they're cooler than the other air. They're magnetically open, and particles of protons, electrons, magnetically charged, stream out in space from these. And if one is pointed to the Earth, and these things reach the Earth, if it's a powerful one, they interact with our magnetic sphere, and we get the auroras from that. Now, if they're large enough, they could electrify our atmosphere. It could overpower our magnetic field and actually come into our atmosphere, and it could actually blow out transformers around the world if one of these were powerful. In the 1800s, there was one of these that was probably powerful enough to do that, but luckily at that time we didn't have a lot of electricity. But if it happened today, it could actually, it could cause blackouts that could last 10 years, could last a decade if they're really strong. They could wipe out all the transformers around the world if they're that strong. So we hope that doesn't happen to us. Now the next layer of the sun is the chromosphere, and that's the thin atmosphere of the sun. It extends about 1,200 miles above the surface, above the photosphere. And it's a very thin and very low density area. And what scientists don't understand is how hot it gets. I mean, the surface of the sun is about 10,000 degrees. And at the bottom of the chromosphere, it starts out at about 11,000 degrees. And when you get to the upper altitudes of the 1,200 mile thick chromosphere, the temperature goes up to tens of thousands of degrees. And we're not really sure. The further you get away from the sun, the hotter it gets. They're pretty positive it's something to do with the magnetic fields, but the mechanism for making that the chromosphere hotter, we still don't understand why that happens or how exactly it happens. Now on this next slide, we're going to talk about the atmosphere. We call the chromosphere, and it's a thin layer. It's about 1,200 miles thick. Very thin layer, very low density layer. And one thing science don't understand is how hot it gets. And we have the surface of the sun. The surface of the sun, the photosphere, is about 10,000 degrees. But as you enter the chromosphere, it starts getting hotter. At the bottom of the chromosphere, just above the photosphere, it's about 1,200. About 11,000 degrees. I'm sorry, about 11,000 degrees. And as you get higher in that 1,200 mile thick chromosphere, the temperature rises to tens of thousands of degrees. And scientists suspect that it has something to do with the magnetic activity that supplies the energy to the chromosphere. But they're not really sure the mechanics of it now. And so this is our thin atmosphere. And it's basically made of hydrogen and helium, mostly, with electrons stripped from the nucleus. It's basically a plasma, this area too. Okay, on this video, I'm going to show you how the loops happen and a solar flare will happen. You see the loops looping around. Like I said, one side is the positive side, and one side is the negative side. I'm sorry. And eventually, sometimes the negative and positive sides, they'll hit each other. And when they do, it causes this big solar flare here. And you see some of the stuff flying off into space. And a lot of it, the gravity and the magnetic field pulling it back in. And that's what's happening in this video here. A very active surface right here of the sun. And on this slide, we're going to show you a mass coronal ejection. And these things we don't want pointed at the Earth. But you see how much material flies off the sun in these ejections, just throwing protons, neutrons, and electrons, all charged particles out into space. And it'll travel the solar system and continue traveling unless it runs into a planet or something. And so that's what's happening here. Very, very awesome sight here. All right, in this slide, we're showing the corona, the outer atmosphere of the sun. It's easily visible during eclipses. Can't really see it without an eclipse because the sun's so bright. But during an eclipse, as we have here, you can see it. And again, scientists don't understand how it gets so hot, but the corona can be up to 2 million degrees, the particles. They're moving fast, the electrons and protons and neutrons that make it up. And a lot of the solar wind comes from these particles streaming away from the sun. And they're streaming away pretty quick, and that's part of the corona there. And next we'll show you a video of the particles coming from the sun, the solar wind. This is a photograph of the solar wind. You see all these particles streaming out from the sun, and these are protons, neutrons, electrons, all electrically charged particles, and they're streaming out, and they constantly stream out. And we see this if a strong one hits our atmosphere, we'll see the aurora from these. But you see all the particles in this slide leaving the sun and traveling out into space. This is a lot of particles. They're basically just the particles of the sun streaming away from the sun. Okay, now the sun is going to be fusing hydrogen to helium for another 5 billion years or so. And eventually the core is going to turn to helium. after the hydrogen fuses into helium. And when that happens, the fusion is going to stop. And when that happens, gravity is going to start crushing that core. Smaller and smaller sizes. That's going to build the temperature up. Right now the core is about 27 million degrees, but when this happens, it's going to rise the temperature of the core to about over 100 million degrees. And at that temperature, it's going to fuse the helium into carbon. And then there's going to be a thin layer around the core, and that's going to be over 17 million degrees. And that layer around the core, that's going to start fusing those hydrogen atoms into helium. And when that happens, it's going to cause the sun to heat up. And when that starts happening, the sun's going to expand into a red giant. The first time it will expand to a red giant. It does it actually a couple times. And what's going to happen is once that core starts fusing the helium to carbon, it's going to be really hot in that core, and it's going to be so jam-packed tight, that it's going to be really hard for that heat to escape. And what's going to happen is the core is going to heat up more and more, and it's going to have no place to expand. And all of a sudden, the core is going to explode. The core is going to explode, and then gravity is going to pull it back in and crush it again, and it'll build the temperature up again. When it does explode, they call that a helium flash. It's basically going to send a shock wave through the star. Probably won't notice it on the surface. Maybe it's some ripples or something, some waves or something. But eventually the core will collapse again, and it'll start building the temperature up to 100 million degrees again. And now it's more stable. It's not jam-packed. It's got room for the heat to escape. And it's going to basically fuse the helium into carbon, and that's going to go on for a little over about a couple billion years. That'll happen, and when then now the sun is going to really expand into a red giant. And on this next slide here, this is a carbon. How helium fuses the carbon. Really easy, a lot easier than the protons fusing hydrogen to helium. And what happens here on the left-hand side, you see you have two different helium atoms. Those are going to fuse together. It's going to release energy in the form of a gamma ray photon, and then you end up with a beryllium. And beryllium is going to have 4 protons and 4 neutrons, very unstable. But really quickly, as I move out of the way here, another helium atom will fuse with the beryllium, and now you're going to have an atom with 6 protons and 6 neutrons, a carbon atom. And also what will happen is to some of those carbon atoms, you'll have another helium adding 2 more protons to make an 8-proton nucleus, which is going to be oxygen. And so the core of the star is going to be fusing into carbon and some oxygen. And it's going to be doing that for a couple billion more years. Now, this next slide here, we get to the surface. And so eventually the core is going to be changed into carbon. And the sun's going to expand. And it's going to be so large on this next slide here. It's a little oblong here, but the sun is going to be giant, and the sun is going to swallow up Mercury. It's going to most likely swallow up Venus, and possibly it may grow large enough to swallow the Earth. A good chance that will happen. And that'll pretty much be the end of the Earth, that it'll be inside the sun, even though life will be long gone, long before this time happens. The Earth will be a livable planet for maybe 1 billion more years out of the 5 billion more the sun has in the helium fusing stage. And so eventually our planet Earth is going to be probably inside of the sun. If not, it'll just be a burnt ember, just basically a rock with no water, no anything. It's just going to be burned. That's going to be the remnants of our star here. And this next slide. Now this is eventually our sun is going to grow so large that the outer layer is going to be so far, and then as as the end of the core starts finishes fusing the carbon, it's going to start pulsating, and that's going to send a shock wave through the sun. It's going to start pushing the outer layers off, and a lot of the outer layers will be so far from the core that the gravity will no longer be able to hold those outer layers. And basically, the outer layers are kind of going to poof off the star, and that's what we have here with the Ring Nebula. You see the remnant of the core of the star right there. And this next slide is another star that, oh, this is the Ring Nebula, I'm sorry, the other one was the Helix Nebula. Really nice to see through a telescope near the star Vega right now, almost straight up in the sky here in September in the evening. And there's another remnant of a sun-like star, and another one in this photo coming up here. There's another remnant. You can see the different layers in this one. This star was pulsing and throwing off layers, and it pulsed again, throw off another layer, so we get this design here. Very beautiful nebula here, planetary nebula they call these. And over time, these nebulas will mix in more hydrogen in our galaxy, and then maybe form some new stars, even though there's not a lot of heavier elements in this, basically a lot of hydrogen and helium in this cloud here, with trace amounts of other elements. And now, eventually, what's going to happen to the core, after the core turns to carbon, the fusion is going to stop, which means the push outward from the heat is going to lessen. And eventually, it's going to reach a point where gravity is stronger, and gravity is going to take that core and basically just crush it, and crush it tighter and tighter and tighter. And basically, you end up with a ball, a white dwarf star, which we have next to our Earth here. It's going to end up, our sun, the core, will end up being a little bit bigger than the Earth, but it'll have almost the sun's mass in it. It's going to be that jam-packed, very, very dense core of carbon and oxygen. And it'll be a white dwarf, white because it's hot. It's going to shine, not very brightly, but it'll shine because of the heat that's generated, that is collected over its lifetime. And eventually, over the billions of years, actually I should say over the trillions of years, this white dwarf will cool into a black dwarf, which will basically be a cool ball core of the carbon and oxygen. And that'll last for basically the end of time, unless it runs into a black hole or maybe another star or something. Could blow itself up in a type 1 supernova. But that's the end of our sun right there. And this will be about 7 billion years from now. That's going to happen. And in a billion years, you think a billion, 1,000 million years is a billion, and this will be around for 7 of those, about 7 billion years. And so that's what's going to happen to our Earth, or our sun, I'm sorry, and it's going to happen to our Earth too, because the sun's going to take care of the Earth by that time. Okay, and here we are back on the Earth, or above the Earth actually, in the International Space Station, looking at our sun and over our planet Earth. And so that's how small stars like red dwarfs live their lives, and stars like our sun. And our next show, we'll get into the larger stars, how they live their lives, and how they basically they're our ancestors, as you'll see on the next show, and how they form all the elements that make up planets and stars and everything, and life too. All the atoms in our body comes from stars and supernovas, and we'll explain that in the next show. So thank you for watching this show. I very much appreciate it. My name is Rick Costello, and I'd like to thank Michael Sinopoli for producing this show. Always does a great job, and I very much appreciate that. And so that is a look at our universe for today, and this is the universe that we live in. And anytime you get a chance to look up. It's a marvelous universe out there. And so have a good day.
Thank you.